Now it's time to build an interesting instrument here. It works like this. Okay, so it measures the rotation rate on the this axis. That happens to be called gamma when it comes to rotation rate. And that follows me when I move my phone in that direction, then gamma rotation rate would be like that. So that makes it quite useful to do like a shakery kind of instrument. And in this example, I use noise, white noise, and I filter the noise with the bandpass filter and move the bandpass filter through the spectrum of the harmonics, but all the frequencies of the noise, and filter out different parts of it, and that makes this sound go like that. Okay, so how is it made? Well, we have a noise element here, and the output of the noise is just white noise, totally random values on the samples. The output of the noise is connected to the bicode filter node, and the type is now set to band pass, and that's the key here. I also use a resonance. The quality it's called Q here, and the higher you raise that, the higher kind of synthier, I would say, it will sound. You can experiment with that. And then I control the frequency of the bandpass filter using a variable that I call F. And the output of the filter is connected to the gain. And the gain of the gain node is controlled by a variable that I call G. Okay, so now let's look at the variables and how they are made. The first one, sorry, that should go away. These are the two interesting ones. So the F variable, the frequency for the bandpass filter, is reading the device motion rotation rate gamma. Apologize for the long name. And I had to experiment quite a bit until I got the useful map in values here for this instrument. And the values are measured in angles per second. So imagine that you turn something 360 degrees on during 1 second of time. Then that would be that would be 360 here. So when I do minus 1000, 1000, that means that I measure a speed of the rotation from a negative speed of 1000 angles per second to a positive value of 1000 sorry, not angles, but degrees per second. All right, so the higher you go here, the higher is the dynamic to sort of you can measure the fastest rotation. If you lower it, you will reach the maximum rotation rate for your interest, and to just limit the dynamics, you could say. All right, this is mapped in an interesting way because I would like the sound to be the same no matter if I rotate it forward or backward. So no matter if it's minus 1000 or 1000, that should map to 4000 Hertz for the filter. So the first value, again, is mapped to the first value here, and the last value will be mapped to the last value. The new thing here is that if the value is somewhere in between, which means that I sort of don't rotate or rotate slower, then it will map towards 100. So we have a mapping curve like that. So if the input is minus 1000, it will map to 4000. If it's towards 0, that will map to 100 Hertz. And then if the rotation rate is 1000, then it will map to 4000. So you could, if you imagine a coordinate system with X and Y, that would create a curve like a V. And that's how we map the negative and the positive rate to the same frequency. And of course, that's stored in the variable named f, and it's used for the frequency on the filter. The gain is used as well, and I found out that to be quite useful, because what I don't want is to have the filter kind of fluttering around when I'm trying to hold my phone still. So I have a gain variable, a g, that is also reading the rotation rate gamma, and it's mapping anything between minus 50 to plus 50, which means that I quickly reaches the upper limit on my measurement, or the outer limits, I would say. So if it's more than negative 50 or more than positive 50, it will just be 1, the first and the last number. So it will be maximum volume. And then if it's in between -5 and 5, which is when I'm trying to hold my phone still, that will map to 0. And anything between -50 and -5 will map to a value between 1 and 0. And anything between 5 and 50 will map to anything between 0 and 1. So that makes a curve like the V, but with a sort of straight line in the middle where it's all quiet and you don't hear any sound at all. If it's between those, kind of, you can look at these as thresholds. So if you move if the rotation is less than 5 degrees per second, the sound won't be heard because the volume will be 0. And this is interesting to play around with. So if, for example, if we raise the outer limits of this to, let's try, maybe not 1,000, but maybe sort of along the way there, like 500, we increase the volume, the amplitude dynamics in our instrument. So I save it, take my smartphone, reload the page, init the sensor, not too bad actually, maybe even better. So it feels more dynamic now. So especially the slow movements are not so loud anymore. So this is definitely worth playing around with those numbers, but this is a good starting point.